Hey everybody, Math by the Moon here today to get you your first video lesson. So this should be a good experience for all of my remote learners who are at home every day, but also for my kids who I'm seeing a couple of days a week. Get you an opportunity to show me what you're doing, so I know you're taking good notes. All right, so some suggestions. When I tell you to pause the video, please pause the video and try to do the work without peeking at the rest of the video as it unfolds itself. If it's going a little bit too fast, pause it so you can copy things down. And don't hesitate to jot down anything on the side of your notes there so that you have little reminders. Sometimes things that I tell you might be important to jot down, and I'll get into something like that here during this video. All right, so we're going to simplify square roots. One thing you already should have in your notes would be the notes on your perfect squares. So if you have that, it should be on a page right before where we're starting now anyway. So you should start with the date, and let me share my screen and you guys can see some of the examples we're going to do and get ready to go. All right, so you should start with your date, and for us it's probably going to be somewhere around 9/8 or 9/9. And write that down along with the title. Our title for right now, we're lesson 1.1, simplifying square roots. So maybe it's 9/8 or 9/9, 20. And we are simplifying square roots. So here's a place where you might pause it and start copying some of this down. Once you have most of it copied down, you might want to push play so you can continue to hear what I'm saying. One thing that's important is to be able to hear what I'm saying, possibly after you've written it. That way you can comprehend the things that you're writing. So some vocabulary words. If you push pause right now, copy it down. And I'll start to talk here. Some vocabulary like the word radicand. I'll refer to that as the number inside the radical. Like down here where this example is, the 24 is the radicand. It's inside the radical. The 128 is the radicand. Perfect square, that's a number that you get by multiplying any number by itself. So that's going to be a perfect square. Simplifying square roots, then, we have two methods. We have the perfect square method, which we're going to do over here with the square root of 24. And we have the factor tree method, which we're going to do with the 128, okay? Generally speaking, if the numbers get a little larger and you can't think of perfect squares, like I said about having that list of squares that we did, that should be the first entry in your notebook, you might want to have that close by. So 24, I'm looking at that list and I'm thinking of a square that goes into 24. The largest perfect square I can think of is 4. So I'm going to split this up into 4 and 6, which, pardon me, I'm doing the wrong method here. I'm thinking of, please don't have that written down. Something just went kaflooey. Perfect. So I'm thinking the square root of 4 times the square root of 6 is what the square root of 24 equals. The square root of 4 is 2, square roots of 6, and that is the simplified version of the square root of 24. Something interesting you could do just to double check your math to make sure you didn't do anything wrong. If you type 2 square roots of 6 into your calculator, you're going to get a decimal. And if you type the square root of 24 into your calculator, you're also going to get the exact same decimal. So that gives you some reassuring feelings that you've done it right. Now, the square root of 128, if you're good, you might say, oh, that's 64 times 2. So you might be able to split it up like that, like we just did over here, and do 64 times 2. If you don't think of 64 being the factor of 128, you might want to run the factor tree method out. So 2 and 64 would be a pair that you would use to multiply, and maybe at that point you just shut it down because you realize you could have done it that way. Let's say you didn't recognize 64 being a square. We're going to keep going all the way down here. 64 is 8 times 8, and 8 is 2 times 2 times 2. That's one of those cubes that we wrote in our notebook. Okay, I like to circle all of my prime numbers, all of my primes. Hide that. So the square root of 128 equals, basically it equals 2 times 2 times 2 times 2 times 2 times 2 times 2. That's the prime factorization. So if we think about this, a square, like over here where we had the square root of 4, that would be because 2 2's made a 4, right? 2 2's made a 4. So for every pair, we're literally saying a pair makes a perfect square. That's something that you might want to jot down on the side of your paper, okay? A pair makes a perfect square. So because these 2 2's are technically the square root of 4, right? That's what these two technically are, because 2 times 2 is 4. That really equals a 2 on the outside. So I'm going to start my answer with a 2 on the outside. Now I'm going to look for pairs, because for every pair, that makes a perfect square. The most common mistake that kids make is they'll take a pair and they'll think that they need to take 2 of them out. Well, that's why I just showed you. These 2 2's right here make a 4, which is another 2 on the outside. These 2 2's make a 4, which is another 2 on the outside. And this guy, you notice, if you counted up how many 2's you had, there was 2 to the 7th, right? So I'm going to jot that down. The square root of 128 was really 2 to the 7th inside the square root. So if we're thinking about this in terms of pairs, how many pairs can we get out of 7 identical factors of 2? Well, you can get 3, right? So there's 2 times 2 times 2, 3 2's on the outside, and then the 1 2 left on the inside. And this will make a lot more sense when we throw variables into it next. So the square root of 128 actually equals 8 times the square root of 2. That's the final answer, because that's what 2 times 2 times 2 is right there, okay? So we have 2 methods. Again, we could do the perfect square method or the factor tree method. And you might have started this out with the factor tree method, but then recognized 64 being a perfect square. If you would have stopped right here, you could have thought, oh, the square root of 64 is 8, and the 2 doesn't have a buddy, doesn't have a pair, so he goes back in. Okay, so now we'll do some examples with variables. We still have to break down the number in the same way we just did with the 2 examples, okay? So we're always going to look at that number first, the radicand, the numerical value first, and try to break that down. So the square root of 18, that's a quick one. The square root of 18 is 9 times 2. The square root of 9 is 3, right? And I'm going to leave some space here. I'm going to leave some space right here because I'm going to think about these variables, and I'm going to put my 2 on the inside. I have 2 variables, so there's a potential to have 2 different things out here. So x to the 4th inside the square root, okay? That is x times x times x times x. And just like we did with those 2's in the 128, for every pair, that makes a perfect square. So I can take these 2 x's and make it 1 x on the outside, these 2 x's and make 2 x's on the outside. So it'd be x times x, or x squared on the outside, which makes sense when you think about it. The square root of x to the 4th is x squared, because x squared times x squared is equal to x to the 4th. The y to the 7th. You might not have to write this all the way out now. You might understand that really all we're doing is taking the exponent. Since we're doing a square root and we're trying to find pairs, you might be able to divide it by 2 and see if there's any remainder. If you divide it by 2, what is 7 divided by 2 without going over, let's say? So the nearest even number to 7 is 6. So really 6 divided by 2 would be 3. So y cubed on the outside. And that would only have accounted for 6 of the y's instead of the 7th one. So that 7th y goes back in. So this would be our final answer. 3x squared y cubed times the square root of 2y. And again, if you're not sure why that y to the 7th did that, here's the visual. Y to the 7th. I'm going to go through and I'm going to circle pairs. There's 1 y, there's 2, there's 3, which is why we had the y to the 3rd on the outside, right, over here. And then this guy, that lonesome y, goes back in. Okay? So yes, you can think of it as dividing the exponent by 2, but don't forget about that remainder. Sometimes there's a remainder. If we would have done the same thing with the x to the 4th, there wouldn't have been a remainder. So the x squared is the only thing on the outside. There's not a single x on the inside anymore. Okay? So then let's try this one together, and then I'll give you guys some examples to try and see if you can do them. Yep, that's the plan. So we have the square root of 180. So that's a little bit larger number. I might not be able to come up with it, but I know it's divisible by 5, and 180 divisible by 5 is 36. Ding, 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 36 is a perfect square. So I'm going to break it apart. I'm going to use red again so I can stay consistent. I'm going to break it apart with 36 and 5. So I intended to do the factor tree method, but I lucked out just like I did on the 128 with the 64 in the second example. So the number side of it, the radicand on the inside would still be a 5, but the number on the outside would be a 6. And again, I'm going to leave some room. This time I have 3 variables. I'm going to leave some room right here. And I'm going to put that 5 back in. So I simplified the 180 pretty quickly. The x to the 12th. If you visualize 12x's written out, how many circles would you have? Well, you'd have 6 pair, right? So that's an x to the 6th. The y doesn't have a buddy at all. Well, I don't want to go past the x to the 12th. There wouldn't be a remainder, so I do not put any x's back inside the radical. Okay? The y doesn't have a pair to begin with, so I have no choice but to put the y in there with the 5. The z to the 15th. I could divide the 15 by 2 to figure out how many pairs I have. That'd be 7 pair. But 7 times 2 is 14, so I'd have 1 extra left over. Whoops, that's actually z, isn't it? Not a y. Crud. That's a z to the 7th and a z on the inside. Again, sorry, I probably broke some of your concentration right there. Z to the 15th, if I divide that by 2, I could get 7 whole and 1 extra. So I put z to the 7th on the outside and that 1 extra on the inside. Okay? So this next slide, I want you to take and copy down the problems. I want you to pause the video and see if you can get these to the best of your ability. All right? There's the answers. If you need me to discuss anything, please bring this notes with you. Hopefully you paused it and did your best at trying to figure it out. If you're trying to look at your work and see how your work compares to my work, please pause the video again and try to do a little problem solving there so you can be prepared for the class activities where we're actually going to be doing the guided practice together. Okay? So again, if you're not sure, you didn't get the same answer I have, maybe I'm wrong. Trust me, that happens plenty of times where I'm doing these problems really quickly. So please shout at me when you come back to school or send me a little email saying, Mr. Moon, you're wrong, because that typically happens too. All right. So then there's some critical thinking questions. Backwards thinking. So it took a pair to make a perfect square. So if there was a number underneath the radical that had an identical pair of factors, we could take one of those out. So now if we're being asked to reverse that process, what did the problem look like? So if there's something on the outside, you have to square it to put it back in. So all these things, it says here to try to figure out what expression simplified into this. So all of these things on the outside here, you know, I keep referring to them as things on the outside. We could call them coefficients. All of these coefficients once were on the inside, but they were squared. They were taking this into figuring out what it was before it was in. So 3 on the inside of the radical would have equal to 9. M cubed. Now remember, I said it's kind of like what we were doing to pull them out. We're dividing by 2. The opposite of dividing by 2 is going to be multiplying by 2. So m cubed really would have been m to the 6th, right? Think about it in reverse now. Pairs, how many pairs can we get out of 6? We can get 3. The n squared would have been n to the 4th, and that's again because we'd be taking 2 pair out. So all of these 3 things that I just put down here inside the square root are going to go back in. They're going to go back in with the 3 things that are currently in there, the 5mn. So our answer, if we build this, we're going to do it in 2 steps. We're going to have the 9, the m to the 6th, and the n to the 4th. That's what we have to put back in for the stuff that's on the outside. And then the existing 5mn. Now, we can clean this up to get a little bit nicer answer on the inside, a little bit nicer radican. 9 times 5 is 45. And when we have like bases, we add the exponents. So there's a 6m and m to the 5th. So that would be m to the 7th. And 4 and n to the 1st would be n to the 5th. So we just pieced this back together, and that would have been the answer. It would have been the square root of 45, m to the 7th, n to the 5th, before it simplified to that answer. Okay? The second one's actually easier than the first. It's saying that this x was something that simplified to 6 root 11. What was the original value of x? So I'm still going to take this 6, which is on the outside, and I'm going to try and figure out what it was when it was on the inside, and it was a 36. So I know what I'm going to put back in. I'm going to put back the 36. And the 11 is still there. So what I'll have to do is I'll have to figure out what this would have equaled. What's 36 times 11?
It's 396.
And that was just me being lazy. I probably could have done that. X, then we know the answer is 396. Because they wanted to know what the value of x was, and the x is under the radical. So a lot of times, if this were a multiple choice question and they offered both of these options, it'd be tricky. But the answer I want is what would have been the value of x, and that would have been 396. So to put stuff back in, you just simply have to rebuild a simplified answer. For a square root, you have to square it and put it back in. Or think of it in terms of, you know, you have variables that were this many outside. That means that they were double that on the inside in terms of their total exponent. So let's see if you can do the same thing with your own example. There's 2 of these, okay? So you can pause the video, copy down the examples, and then see if you can get them. Again, after you check your work, if you didn't have something correct, and you could look over my work and see if it helps you piece it together. And if I did something wrong, just tell me. And if you have any other questions, bring them to class with you and we'll go over it. Okay? So pause the video, try these 2 examples. And here are your answers. Hope you have an excellent day. Hope you have the excellent first time at going through notes for math class. I think this is going to be the best way for us to try and flip the room around. So the lesson you would normally get is the actual homework. This is going to be easier, time better spent. So when you come back in here, I can have you working on things to address what you didn't learn from the video. So I think this is going to be the best use of our time. As always, let me know if you need anything. You have all my contacts. Later.